Reduction formulas, it's another example of in maths we look for patterns and then use patterns to our advantage. It can save us time, and that's what a reduction formula does. We often use it to reduce the powers in our integrals, because as we saw with our trig ones, when it got to a high power, often we had to use lower powers to solve the higher powers, so we had to find several different integrals to do it. Well, a reduction formula can solve that problem. The vast majority of these questions are done by integration by parts. Now here's an example of one here. Now we're going to find the integral from 1 to e of x log x cubed, but I'm going to create a reduction formula for this. So I'll let u equal log x to the power of n. It's the logical thing to pick for a couple of reasons. One, we don't have to integrate the log, but two, it will reduce the power. It'll bring it down. So n log x to the n minus 1 over x. dv will be x dx, which means v is a half x squared. So we get uv minus integral v to u, and we can see the power has gone down by 1. It is still the same integral essentially. Substitute into the one on the left and we come up with our formula. So there's a nice neat formula. In is e squared on 2 minus n on 2 I to the n minus 1. So not only can we now find our question, should we have any other question that looks like this to different powers, we can do it quite easily. Our integral becomes I3. So substitute in, we get e squared on 2 minus 3 on 2 I2. Alright? But I can now use the formula for I2, which becomes e squared on 2 minus I1. But I can use the formula for I1, and it becomes e squared on 2 minus a half I0. I0, I don't use the formula for, I now turn it into the integral, because now I have log to the power of 0, which is 1, nice easy integral to find, and that's just x dx. And eventually, let's tidy that up a bit, there we are, e squared on 8 plus 3/8. So that's the idea of the reduction formula. Imagine if we didn't have it, then we would have had to do integration by parts, how many times there? 3 times? At least 2 times we would have had to have done it to solve our problem. Another way you can evaluate, see I've done it by reducing, going from I2, 1, 0 and so on. Some people like to build it up and start with the I0. And so I0 is a half e squared minus 1, and then plug that into the formula to get I1, then plug that answer into the formula to get I2, and then plug that answer into the formula to get I3. It's really just a preference whether you prefer to build it up or reduce it down. But either way, you get the answer. So integration by parts, as I say, that's the most common way of doing it, but not always. Trig ones particularly. See, I've got cotan to the power of n. And you'll recall our technique for tan, which is the same as cotan. We did the same technique every single time. So we'll just use that particular technique. So cot to the power of n, what was that technique? Well, we extracted out the cot squared. The cot squared I can change to cosec squared minus 1. Split that into 2 integrals. One we can solve using a substitution. The other is the same trig integral but to a lower power. Working out the first integral, there it is, we have our formula. So we can now work out I6 or cot to the power of 6. Another way we could do it is this. It doesn't happen all the time, but sometimes if you got these powers differing by 2, and certainly when you have trig which involves a lot of squareds, it certainly works really good when they say things like show that this is this. Okay. Because then I could say, oh well hang on, now let me work out what in plus 2 is using the formula they gave me, because I'm showing it's going to work. And I substitute in, there's the 2 integrals, pull it together to one thing, then I notice a common factor, oh I'm left with 1 plus cot squared. Cot squared is cosec squared, and I can integrate that, and so I can rearrange it, and I've got the formula. So that's quite handy, especially in show that ones. It can often work. Alright, well let's now go and find that I6. We've got the formula. So substitute it in. It's reducing by 2 each time, so I now have I4, I2, I0, and then I'll just integrate I0, which is integral of dx, and we get minus x plus a constant. Another thing that can work, algebraic manipulation, that idea we saw with integration. And that's how I'm going to do this one. Given that this is our integral, find the formula, and they've told us it's going to connect in with n minus 1, so we know it's reducing by 1. Okay, that's what I'm working with, right? So if I'm reducing by 1, makes sense, make u equal 1 plus x squared to the power of n, so du will be that, dv therefore is dx, v is x. So we get uv minus, now have we got, no, see we still don't have an in, this x squared's here, that's where the algebraic manipulation is going to come in handy. So I'll rewrite that x squared as 1 plus x squared minus 1. Then I can split that into two integrals. Now that first integral is actually to the power of n, but now you can see it's in the form of the in. So I can sub in, I'll move that 2n in to the left hand side because I'm now looking at it like an equation, and divide by 2n plus 1, we have a formula. It's nice when they tell us what the formula is going to be because we know if we got there. When they don't, like this one didn't, they just said find one, you're always a bit unsure. Is that what it is? Or yeah. Let's have a look at some past ones. Whoa, 1987. They've told us what we have to prove. That's nice. I guess in an assessment, they're more likely to tell us it, because if you can't get it, the following part's usually going to be, oh, heads go and find this. Or at least if they've given you the formula, you can show them, well, I know how to use the reduction formula. You can get marks for that. Whereas when they don't, I suppose you still get marks. You're just subbing it into the wrong formula. But you can still show you know how to use it. Okay, so cos to the power of n. Now we had different techniques, didn't we, depending on whether the power was odd or even. So how will I do this one? Well, split it into two, and I'm going to have to do it by parts, I think, because as I say, I don't know which technique to use. The one for even numbers, the one for odd numbers, I don't know. So there's du, dv becomes that, v is sine x, subbing that all in. Now I've got to try and get something that looks like in. I got cos n minus 2x sine squared. Sine squared I can turn into 1 minus cos squared, get everything with coses. I'll also work out what's in our brackets over here. Is that just 0? It is, isn't it? Because cos pi on 2 is 0 and sine 0 is 0, so all of that's 0. Now back to our integral, split it into 2, and they're both in the form of in. So yep, I've got n minus 1 in minus 2 and n minus 1 in. Bit of algebra now, move terms around and we get what they want. Of course this one here, they've told me the answer. It involves trig. Okay, so it's probably a good chance I can try this idea. Let's have a look at in minus 2 minus in. Let's see what happens. Rubbing that in, it all comes down to cos n minus 2x times sine squared. If I do u equals sine x to u equals cos x, I really haven't saved myself a lot of time this one, because I'm still going to have to use integration by parts. So whilst the idea works, wasn't necessarily a quicker way of doing it. But let's keep going through just to show, yeah, we do get what we want. There we go, playing around with the algebra on that one, and we come up with the formula. Right, the question was to go and find cos to the power of 5, which is I5. That would be 4/5 I3, which will then be 4/5 times 2/3 I1. That is where I'll stop on this one, because I can't reduce by 2. I negative 1 doesn't make sense. So cos x dx becomes sine x 8/15 is our answer. That one was from the very first year I taught. Let's look at the last year that I taught, 2022. Oh, this was a beautiful, beautiful question last year. I don't know if you've seen it or not, because it combined so many of our different topics into one question. It has several parts, but let's work through it. Jn, see, you don't have to use I, they can be creative. J instead of I. Jn is this integral. N is a non-negative integer. Wow, gift mark. Show that J0 is 1 minus 1 on E. Well, J0 is just e to the minus x. That's like a 2-unit integral we're getting marks for here. We want to hope we get marks for it anyway. So that's minus e to the minus x, sub in. Yes, we got 1 minus 1 on e. Thank you very much. Mind you, it could be a signal for the rest of the question. We're going to give you a mark here because good luck. Show that Jn, so now we get inequalities into it. Show that Jn is less than or equal to 1 on n plus 1. Okay, here's how I did it. Well, I know x is in between 0 and 1, because remember our integral is going from 0 to 1. Well, if that's the case, then e to the power of minus x must go between 1 on e and 1, because I know e to the minus x, that curve is continually decreasing. So therefore, I can reverse the inequality signs. That's what I've essentially done here, because I've taken every piece and said e to the power of that. Well, e to the power of 0 is 1, so it's over the right hand side now because I'm swapping the inequality signs. E to the power of minus x goes in the middle, and then e to the power of minus 1 goes to the left hand side. So remember that. If you've got a continually increasing function, you can sub it into that function, the inequation will still be true. If it's a continually decreasing function, sub it in, you're going to swap them around. It all comes to do with the diagram. If you think about the diagram and when you sub in, what would happen to the y values in compared to those x values. Okay, so I've now got that. Now Jn was this particular integral. So therefore, the area under that will always be less than or equal to the area under here, because I'm now saying that e to the minus x is always less than or equal to 1. So I'm multiplying by something that's always less than or equal to 1. So this must be below that if I was to draw these two curves. I can work out that right hand side, and we have our result. So part I, gift. Part I, you got to think about that one. Part 3 then. We're going to create a reduction formula. Okay, there's our integral. I'll let u equal x to the n. That means to v is e to the minus x. uv minus integral of v to u. Yes, the second term there is in the form of the, so I can call that n times j n minus 1. Play around with it. Got the answer. So 1, thank you very much. 2, 3, okay. Using parts 1 and 3. Show by mathematical induction. Now we get induction into the question. So show by induction, or otherwise, if you really want to do it a different way, you can do it a different way. This lovely, lovely expression. Jn is equal to n factorial minus n factorial on e times the sum of all of these terms. 1 on r factorial going from r equals 0 to n. Alright, so that's what I have to show. Prove the result is true for n equals 0 is the first case. Okay, well J0, using the formula they just gave me, would be 0 factorial minus 0 factorial on e, going from r equals 0 to 0 of 1 on r factorial, which is 1 on 1 minus e. Yes, it is true for n equals 0. I'll assume it's true for k, so I'm going to assume that works. We now need to prove it true for k plus 1. So everywhere I see that k, I'm changing to k plus 1. This is what I have to now prove. Got to get the assumption in there, but we had an assumption, we assumed what jk was. So plug that in. K is going to involve a little bit of nice manipulation. Well, the first bit's nice. K plus 1 times k factorial is k plus 1 factorial. I've got that bit. It's now this sum that I have to create. So I've got the sum going from 0 to k times that k plus 1 factorial on e, but then I've also got this standalone term minus 1 on e, which somehow I've got to get into that, and we will create what we want. The 1 on e, I'm just playing with the 1 on e because I need to pull it into the sum. So I need to somehow get this k plus 1 factorial on there. So I've made it k plus 1 factorial on e, but to do that I've got to multiply it by 1 on k plus 1 factorial. I haven't touched the sum yet. Now I've put that term into the sum, because that would be the k plus 1th term of this. Right, so you've got the 1 on k plus 1 factorial, and it's times by the coefficient of the sum. So I can now pull that standalone term into the sum. And that was what we were looking for. So hence it's true for k plus 1 if it's also true for k, and since it's true for 0, and so on and so on. Okay, didn't stop there. Now use parts 2 and 4 to prove that actually that sum is simply e. It's an expression for the irrational number e. Well, let's go back to what we worked out before, because it said use parts 2 and 4. And in part 2 we showed that Jn was always less than or equal to 1 on n plus 1. I've also put the 0 in there because we know it's positive as well, so I'll throw the 0 there. We've just turned out, or what we've just worked out, that Jn is that expression. So that now I know is in between 0 and 1 on n plus 1. Hang on, I've just divided everything by n factorial. Divide 0, we still get 0, but on the right hand side, if I divide by n factorial, then the n plus 1 has now become n plus 1 factorial. So we now know that. Well, let's investigate the limit, because that's what they want us to do. The limit as n approaches infinity. Well, I didn't bother putting it on the left-hand side, because obviously the limit of 0 will always be 0, but I'm going to find the limit of these things. Well, the right-hand side, let's just look at the right-hand side. I'm substituting infinity into something that's on the bottom of the fraction. Well, that's got to be 0. I have now trapped that in between 0 and 0. So I now know that that is equal to 0. Well, move the e to the other side. We have now shown our sum is equal to 0. What a great question last year, eh? 4H.